Anyway, so, yeah, it's not the end of the world. The sky has not fallen.
You sure about that?
I promise.
Because there is no contacts.
Not the end of the world. I really try to be as straightforward as possible on these things too. I don't know how to, but it's one of those things. I want you to think about things too as you go through this stuff, right? I could, I could put a bunch of stuff on a test that all you have to do is regurgitate. Just spit it out, where you just memorize a bunch of stuff, but you never learn anything. You know what I mean? And it doesn't do you any justice doing that. It cheats you is what it does. When you start having to memorize all this stuff. Because you get out of the class and you're like, I didn't learn a thing in that class. You know what I'm saying? You guys have been there. What I would like to do though, I want to go through this test line by line and make sure everybody's got the right answers. And I want to just go around the room, if you don't mind.
How do you I/O modules connect to the processor and the modules or PLCs?
Shouldn't really elaborate on that.
By slot.
Yes. The back plane. Number 2.
What do the PLC logic look like? What do the individual symbols represent? They represent instructions, and what do the numbers represent addresses?
Yeah, did anybody have slot and terminal number on B, 2B? Slot number, terminal number? Or word number, terminal number? Word number, bit number?
Bit number?
Bit number? Did you have word number?
No, of course not.
Let me give you credit for that. There's another one on here I'm going to give you credit for if you have another answer. What is it? Number 21. Look at number 21.
Yeah.
Did anybody put inputs and outputs?
Yeah.
Yes.
Okay, I'm going to give you credit for that. But we're going to go through the test first, and then I want you to come up and I'm going to do it right now. If I don't, I'll forget about it and it won't happen. Where are we at? Oh, number 3, ready?
What type of PLC was ladder logic written for question 2? Fixed.
Fixed. How did you know that?
Because slot number was 0.
Yeah, good.
Number 4, how do you determine your answer in question 3? The input is 0 and the output is 0. That's the address for the input and output is 0 after the colon represents card number, which in this case is.
Yes, good. Yeah. It's got.
Describe the operation of a discrete device. It's either on or it's off.
1, 0, true, false. Yep. There you go. Aaron, please.
They normally open proximity switch is connected to a syncing input module. If the system control voltage is 24 volt DC, what voltage would you measure on the input when the proc switch is made? Calculate 24 volts.
24 volts. Yes. Why did you do that? Why did you put 24 volts? Why would it be 24 volts?
Oh, I just remembered using it another day, so it's
What you did?
Memorize.
Why is so we have a syncing input module. What's that mean exactly? Syncing input module. What's a syncing input module supply to the device? Why is it common to the device? That means the device is connected to what? What level? Yeah, what voltage level? 0 or 24?
Oh. The syncing would be 0, right?
So the module is supplying 0 volts. It's supplying the common
Right.
to the device.
trying to tell us why.
Yeah, so the device has to be supplying 24 volts. Yeah. Where we at? Number 7, okay.
What value will be in the input image table? 1.
Yes, good. Aaron, what do you remember?
If a normally open proc switch is programmed into your PLC logic as an XIO instruction, and then the proc switch is made, what will be the state of the instruction in the logic? 0.
0. How did you figure that out?
I read it. Let me read it again and I can tell you.
How did you think through that?
Because if it's normally open, and then if it's an examine if open instruction, then whenever it's, if it's closed, then it's gonna do a 0 because it's only examine if open. When you close it, or whenever it's open, it's a 1, closed, it's a 0.
Yeah. Did everybody get the right answer on that one? No? Let's go through it. So let's work through this one. So you know exactly how it happens, why it happens, and when it happens.
I get it.
You get it? Okay. Actually, I was gonna have you come up here and work through it, since you got it. No, I wouldn't do that, did you?
So you were gonna work through it?
Yeah, let's work through it, yeah. That way you know beyond a shadow of a doubt, hopefully, how it actually works. Because you don't want to just say it's a lucky guess, you know, you don't want, yeah, it's a 50-50 chance. Right? Like a lot of things in life, it's a 50-50 chance, you got a 50-50 chance of walking out here and getting hit by a car too. We don't want to do that, but you know what I'm saying? A normally open proc switch is programmed into your PLC logic as an XIO instruction, and then the proc switch is made. So it's normally open. What will be the state of the instruction in the logic? And you know, if you're in doubt, whenever you're in doubt, draw this thing. Get a normally open proc switch. I'm not very something like that. Normally open proc switch. There's the XIC. There's the XIO. And let's see. What's it say? When it's made. So when it's made, what do we have? What voltage level do we have on the input? It's made 24 volts. And what is that in the PLC? What value? 1. Which instruction is going to be true?
The examine that open.
The 1. Which one's going to be true? Yeah. So this one's going to be true, right? Everybody get that? Because we want logic continuity, right? And then what's it say? It says, what will, in XIL, and then the proc switch is made. What will be the state of the instruction in the logic? Yeah. Right now we have a 1 in the PLC because the proc switch is made. And the XIO requires a value of what to be true? 0. Yeah. Good. Yes.
Explain the difference between a unipole analog module and a bipole analog module. Unipole only positive direction, one direction, and bipole is positive and negative, 2 directions.
Yes. Mr. Thomas.
You were troubleshooting physical working carries out the margin using the electrical print below the light is on for output. 1.7 for S2, but 420 is not energized. What is the problem called? I had I didn't know, I missed this one, I had A, but I didn't see that answer to C. You might explain it better than I can, 'cause I missed it, you know.
Oh, yeah, that's fine. That's fine. So just looking at the electrical print, what type of module is it?
Sourcing,
Yes, how did you determine that, Scott?
because I got sinky drawn.
Exactly.
Because it's supplying current.
Where from? I can't see.
That's what I'm saying,
All those outputs there, those are,
They're receiving current, so they're sinking.
so it's wired up like this. This is an output. And so I'm just gonna do this control relay. 420 CR. Whatever this one is, 421. Yeah, so where are all the loads connected to? Where are the output devices connected to on the drawing?
Like, come.
Yeah, that's right. They're connected to common, aren't they?
Okay.
So if they're connected to common, you know, to energize one of these, what's the module supply?
Supplying current.
Yeah,
So it's sourcing current.
yeah.
What threw me, what is those addresses right after output, 0172?
Those are PLC addresses. That's saying that car is in slot 1, using word 7.
So that's not actually an output itself.
It is, yeah. That old colon 1 dot something there.
See, that's what threw me, I thought it was going directly to an output device and then to
Gotcha. And I guess another clue is it says slot 1, rack 0, group 6 on that model, right above it. So it tells you it's a module in slot 1, rack 0, group 6. So let's see. The question was, what is the problem? You're troubleshooting, and here's another key. It's a previously working output module. The light is on for the output. In other words, you look at the module, the light's on, right? On the PLC output module. Let's see. But 420 CR is not energized. What does the problem cause? This is a syncing output model. True or false?
True. No fault. It's a source.
It's a source.
It's a sourcing model. B, so this is a sourcing model. Does that have anything to do with this relay not being energized? No. So we can eliminate those two. How about D? Is that pretty easily eliminated? 420 CR is improperly connected. Does that have anything to do with, because it was previously working, right? It was working previously.
No, if it was working, that's unless somebody went and changed it.
Unless somebody's been thinking around in the pan. Exactly right, which they should be, right? How we get out of the pan. So the only really thing you have left is C. Output PLC is bad. Does it make sense? Down sort, hopefully. Where are we at? Number 12, Adam.
What was the answer for 11?
Sourcing.
Disregarding the addresses, design the PLC logic for the hardwire relay to logic below.
Did you get it right?
Yes, I did get it.
Okay. You want to draw it up here?
Not really, but I will.
Thanks for coming up here and doing it.
How do you use this assessment? Good enough?
Yes, that's good enough. Now, how did you come up with that? Explain that.
Because pretty much everything's gonna be hoop and contactors unless it's a control relay thing.
Because you need logic continuity on PV2, right? Yeah, I think a lot of you got this. LS, the limit switch, you've got to have logic continuity on that for the power though. Push button 1. Yeah. And another part of this, you need to kind of understand how the relay logic works too, right? You got to go through it and figure out how the relay logic works. And I think, does the control relay logic make sense? Here's the control relay. We have a seal in it. So if we're energizing this thing, here's our PLC logic. Same, the very same logic as the hardwired logic. What's the Boolean equation? Where are we at?
Parentheses A plus B parentheses C.
We got right on the board.
We'll get right on board.
Yeah, but we don't see it.
Well, I mean, you understand what I'm saying.
Yeah.
I don't.
Right on the board.
What was it?
Here you guys.
Say it again.
Parentheses A plus B, close parentheses, open parentheses, C times D, close parentheses equals 1.
Yeah.
You got that on the board?
Yeah. So some of you, I've noticed some in some of the class, I don't know if it's this class, but some people are getting the or and the and mixed up, the plus the time sign or whatever, for whatever reason. So and is always a time, multiplication. And really, well, I don't know. If you got this right and you used your PLC logic for the Boolean equation, you're good to go. I did it without doing this. I looked at the circuit first.
I got 1.
So it's A or B.
I knew that was supposed to be open, but somehow it was closed.
C and D.
50.
We all have things like that.
A or B. And C and D.
That makes no sense. It's not logic.
So you use those control relay contacts?
Yeah. Yeah. And it's just the logical equation for the circuit. I guess you kind of want to just disregard what kind of devices they are.
You call the guy over here for no reason.
It really doesn't matter. There you go. You're just looking at the logic and how they are. Where are we at? Fitzgerald. All you.
What, huh? I'm lost, what, huh? Which problem?
Call that job.
14.
Thank you. 14, write the Boolean equation for the following logic gate circuit and design the PLC logic.
Got right forward.
I got around the board. So you quick. Cool, thanks.
Yeah, I said,
Alex, thanks you first.
I'm sorry, I just noticed that.
Oh, that's cool, man.
I don't think he wanted
The
to.
voting equation would be A, B plus C, that's C nine, yeah, C nine. And then D equals Y.
Good.
And then the logic, the circuit itself would be I have raised it.
It's,
Okay, well, then, yeah.
there we go.
And that's the C.
There's the deal. Sure.
Ta-da!
Good job. 15.
Awesome.
Oh, Marcus, I'm sorry. I didn't mean to leave you out. Number 15, please.
There you go.
PLC sends the following data string over to another PLC. You're only to read the data string.
You don't need to.
All right. If the PLCs are using even parity, then the value of the parity bit will be, I said it was 0,
Yeah, why'd you say it was there?
because the number of ones is already even.
Yes, that's exactly it. Good. Yeah. All right. Number conversions, we're not gonna go through that stuff. I think everybody should get on that. How about 18? For some reason, people missed that. I don't know why. Yes.
Describe the sequence of operation or steps of the PLC for one program scan. Note, include all steps in the correct sequence. Step 1, scan inputs. 2, execute the program. 3, update outputs. 4, housekeeping, diagnostics, and communication.
Yes. Star, number 19, please.
A manual code switch is connected to a 24-volt DC switching input line. The switch is in its normal state. The logic for the code switch uses an XIC instruction, but the instruction does not have logic for failure. The flow switch has gone bad and it is open.
Yes, figure that out.
But I got it wrong.
It says that, now keep this in mind, it says the switch is in its normal state. What does that mean exactly?
That means the contacts will already closed.
Yeah, it's exactly what it says it is, yeah, that's right. Switch is in its normal state, that means they're gonna be closed. Let's go through it. There were a fair amount of people got this wrong. I don't know if it was this class. It says an only closed flow switch is connected to a 24-volt DC syncing input module. Draw it out, guys. Draw it out. You're in doubt. Only closed flow switch. It's a syncing input module. So what's that mean?
It's receiving current.
Yeah, it's receiving current. That's right. So what's that mean for the device? What does it need to be connected to?
the flow switch.
The device needs to be connected to us.
This is a syncing input. In other words, you're gonna have, there's gonna be a terminal on this module that's connected to, that's exactly right. So it's a syncing input module. So where's the device need to be connected to?
The voltage.
The voltage, yeah. Voltage, that's right. It says a switch is in its normal state, okay, we'll go with that. The logic for the float switch uses Ch6 instruction. Here's the logic. Ch6 instruction. But the instruction does not have logical continuity. So right now, while it's in its normal state, what voltage are we going to measure on this terminal, on this input?
24.
Yeah, 24 volts, that's right. Value in the PLC? A 1? Yes. It says we have this Ch6 instruction, but it does not have logical continuity. A, can we eliminate that? It's a normally closed, whatever, normal for a normally closed switch that uses Ch6. No. B, the float switch has gone bad and is shorted. Does that make sense? Does B make sense at all? The float switch is already closed, right? If it's shorted, that means it has done this somehow.
Yeah.
Shorted the contacts or welded themselves together or something. So we already have that as it is. The float switch has gone bad and it is open.
I disagree with that. I think it's more likely that the instrument's going to fail in the PLC than the mechanical switch will fail. So I think more likely D is the correct answer, is my opinion.
D's not an option.
D is none of the above.
The float switch has gone bad and is open. We probably have a lot of electronics out there these days, electronic float switches, but they go bad. But you've seen the old ball type float switches too, they got a cord, they're hanging down, just like a toilet, or in your toilet tank, kind of sort of. I'll tell you what though, we had a sump where I used to work outside of the plant. It failed. So good. It failed. And we ended up putting two float switches on the backup. It poured water and oil all over the place. And Oceanside, they didn't like that. EPA came out. So we had got oil down in this little pond right here. Shut your plant down, big time. Let's see, number 20.
A normally open pressure switch is connected to a 24-volt DC sinking input module. The switch is in its normal state. The logic for the float switch uses an Ch6 instruction, but the instruction does not have logical continuity.
What's the
That's how a normally open switch works that uses an Ch6.
good thought process? You didn't get it?
No, sir.
Okay, good. You got a 25% chance. Mr. Reed.
The input and output data files are a direct copy of the input image table and output image table of the PLC.
Yes. If you had inputs or outputs, I'll give you credit for it. 22, Scott.
Which PLCs use what basic logic function and or not?
And or not, yes. And the key words were logic functions, right? Logic or whatever, yeah, logic functions. Logic said OTE, XIC, XIO. Those are instructions. That's the difference. Instructions versus logic functions.
What was 21 again?
Input image table and output image table. And then 23, Aaron.
Do you mean to like just tell you the numbers?
Yeah.
Okay, so the first
Yes. Did everybody get that right?
Yeah.
I just know, but. Do you understand how it works, Barry?
Yes, sir.
Okay. So, on 21, if you had inputs and outputs, come up here and
Touch it a little bit.
we're not gonna get real deep into it since it should be reviewed.
I'll be honest
Should
with
be
you.
reviewed, hopefully.
Hold that.
No guarantee.
We didn't really have such a discussion.
I got it.
We said anything about memorization?
So, the common control, output control devices, motor starters, control relays, contactors, so on. Well, that's probably the four most common types of output control devices. Tell me this, and I know everybody knows it, what's the difference between a motor starter and a contactor?
Have a higher coil and amperage of current.
Difference between motor starter and contactor. And yeah, motor starters have overload, so, yeah. And you guys that are in the factory, working in maintenance, you're gonna hear all the old timers call everything contactors, don't you? Everything's a contactor. Like, they used to say, the guys I used to work with, yeah, everything's a contactor. I said, that's not a contactor, it's a motor starter. You got it, there is a difference. And another part of this, in the Siemens world, all relays, they call all relays contactors in the Siemens world. I don't know why. You're around the BMW world, so you're around a lot of Germans, I'm assuming, so they call everything a contactor. But yeah, there is a difference. There's motor starters, there's contactors, and there's control relays. The thing is, so we have motor starters and contactors. Contactors are used for really, really high current loads, right? High voltage, high current loads, like heaters, huge heater coils, that type of stuff. Or huge lighting banks and that type of stuff. I don't know if you guys have seen any of that. Let me show you. First of all, let's take a look at a motor starter. This is an old school, I want to say, motor starter. That's the stuff we used to use back in the day. And it has overloads, but they're actually heaters, right? You've seen the heaters in a motor starter? Yeah, it's, what's the material that's called inside here? It's like Eutectic? Eutectic. I can't remember that name. It's some kind of a solder. Solder pot, or whatever you want to call it, yeah. Eutectic alloy. So yeah, so everybody, you guys probably know how it works. What happens if one of the legs of the motor starts drawing too much current, it heats these up, right? It's going to heat whichever one up, it's going to trip. What happens is it melts the solder, or the eutectic alloy, inside this thing. There we go. And then it trips this little spring-loaded set of contacts in here. Have you guys pulled one of these apart? Hopefully you don't have any.
Well, we see parts of in Anderson Robotics class. He's passed parts of the line.
Okay.
Well, you can, but Anderson touch basically.
Would you put pilot lights on that as a common output control device?
Yeah. You guys would have enjoyed that quiz from yesterday. It was a good quiz, wasn't it?
Yeah.
All I did was wrote the name down. I wouldn't.
I believe Andrew's talking about his new truck.
Tell you what, it'll reel you in. You gotta watch it.
I don't want this.
It'll hook you. Trouble hook.
He says, he drove it yesterday and I was like, I didn't know you had a new truck. He's like, yeah, I think I heard something about it. I was like, why? He's like, it's a 2009, it's a 2008. I was like, all right, thank you.
Put Linus in. So yeah, motor starter. Motor, the old time motor starter with the heaters. There's probably still some of them out there. Actually, back years ago, when I went through all that stuff, the classes that I was in, we would have to size the heaters according to the motor size and all this stuff. We looked at the specs of the motor. Then we went to the tables of the documentation, size the heaters, size the motor starter. We went through every little detail on sizing everything to run a motor. But I know they don't probably get into that these days. There you go. And when I taught motor controls, I taught that too, to the classes here. The new style, as everybody has seen, everybody knows, overload relay, and it's adjustable from this one, this particular one, 1 amp to 5 amps. I can't see it, but I think that's what it is. 1 amp to 5 amps. Something a little bit better. So contact with the motor starter. While we're on the subject, let me show you a great example in a set of electrical press. This is a set of electrical press for a parts washer. Good size parts washer. Probably from here to the side of the building over there. And huge. Yes, good size parts washer. So we have all these motors, right? Motor, pump motor, rinse motor, phosphate pump motors and all this stuff. And if we look, here's the motor starter contact, right? That's not the motor starter itself. Is that the motor starter? No. That's not the motor starter itself. And we're going to go through this a little bit to kind of show you how to follow the roadmap. Kind of an introduction on following the roadmap of electrical press. It's one of those things that will be very important for you to be able to do in your troubleshooting stage. Wash pump motor. So here's a motor starter, and you see where the overloads are. And I would venture to say that this was adjustable, right? Overload setting 22 amps. They've already adjusted it. It's probably something similar to this. Would be my best guess. And then, if we look at the motor starter contacts here, there's also an auxiliary contact, right, off of that motor starter. You see the dashed lines right here? That means that's all in one package. That's enclosed together. Same way with the dashed lines around the breakers, circuit breakers, and the overload. So you have overloads and circuit breakers all in one package in this thing.
Now, things that are grouped together like that, that's going to depend on the component price and how it comes.
That's right. Yeah, that's exactly right. If we look at the auxiliary contact, where's that going to in this thing? If you're troubleshooting this problem, some problem with this thing, yeah, that's exactly right. It's going to the PLC. How'd you figure that out, Terry?
Input separate the slash separate.
That's exactly right. Yeah. It's not a rocket science, is it? You didn't know this a month ago, but yeah. Yes, good. That's exactly where it's going. And if we want to know, let's say we want to know what kind of voltage is supposed to be on that input of that PLC. How do we trace it back? How do we trace it down? reference 1100 overload, we could do that. Well, they're coming this, yeah, it's coming this direction, isn't it? What's the 619 telling us? Anybody know? It's a line number, yep. It's telling us, it's on sheet number 6 of the electrical drawings, line number 19. Let's look at the print that we're on right now. What sheet are we on right now? Yeah, we're on sheet number 2, lines 2, 3, 4, and so on. So if I go to sheet 6, line 19, 6, line 19, and I should be able to figure out what's going on here. Did anybody notice the wire number up there? Let's look at it again. Wire number. You see what the wire number is?
P261.
Yes, P6170. I'm gonna go back to our sheet. 619. There's line 619. Let me crunch it down so you can see the whole drawing, and then I'm going to zoom in where we can see 619 a little bit better. There's that wire number P6170, and it tells us, what's this telling us? Up to 700. Anyway, so we trace it back, right? What kind of voltage is going to be on that?
24.
Yeah, 24 volts in it. Exactly right. When you open up a set of electrical prints, the first few drawings in there, first you're going to have the index, right? The index drawing is going to tell you, that's kind of your roadmap, where all the devices are located. And then the first few sets of the prints, the first drawings after that, are going to be the power circuit. That's all your high voltage stuff, 483 phase coming in, and your power supplies and that type of stuff. What's the rest of it going to tell you? After all the power circuit stuff, what's the remaining pages going to tell you? Control circuit. It's going to have the control circuit stuff in it. All the control circuit. So you have power circuit and control circuit. The low voltage stuff is the control circuit. It's either 120 volts or 24 volts. Let's see, motor start. And let's continue on. Technically, they didn't do these drawings right because they put some more power circuit stuff down below all that. And here are the contactors that we were talking about. Contactors. No overloads, right? No overloads found. How's the heater, how's this stuff being protected? We have overloads and circuit breakers on the motor starters. How's this being protected? Yeah. Yeah, that's exactly right. Yeah. Everybody see that? Fuse 1602, 45 amp. Yeah. Pretty high current. And if we wanted to find out where the coil is to this contactor, where do we go?
Reference line 29, and then 11 to 21.
Yeah, well, okay, so there's the auxiliary contact, right? Off of this contactor. It's going into the PLC. It's probably saying, hey, I'm energized, or my contacts are closed, or something. And we'll be going through the PLC program for this also a little bit later on. So where do we go to find the coil for this contactor? Yeah, 1521. So it's on sheet 15, line 21. 15, there's 15, 17, line 17. And they mislabeled it. So this should say say 1521, don't get confused by that. 1521, and yes, there's the contact report. And then we continue to trace this thing back, right, in our troubleshooting efforts. There's just a contact sitting out there that energizes the contact. CR10/2. Not a real good reference, but if you look a little closer, there's a reference number right here, right? 1322. So we go to sheet 13, line 22. $13, $22, $13.22. How does it get energized? How does that contactor coil get energized? CR1002, I believe.
The X10 2 is activated, right?
There's the coil for the contactor. We know it goes to a terminal block, right? TB1, that's a terminal block that's inside of a panel somewhere. What's this tell us?
Output.
Yeah. Output, isn't it? PLC output. See what kind of module that is? 16-point relay output. So yeah, it's being energized by the PLC. What's 16-point tell us?
16
Yeah, 16 outputs. Yeah. Or 16 terminals. There's the terminals on the module itself. Yes, one word. One word. Good. Anyway, to give you somewhat of an idea of, hopefully you'll all be experts at reading electrical prints by the time this thing is over. Although this class, I really don't get into it that deep. Troubleshooting, we hit it really, really hard. What else we got? Control relays, motor starters, contactors. And then we get into input devices in this thing. And some of those include proc switches, limit switches, photo eyes, photoelectric sensors, that type of stuff. Proximity switches. What are the two types? Inductive. Capacitive. What's the difference?
Inductive uses metal, passive, and physical passive motion.
Yeah. Inductive type proc switches detect metal parts, right? Metal objects. Passive, pretty much anything except air, right? Anything's, pretty much anything. Can you see the advantages and disadvantages of using one or the other? Yeah. So if, let's say we have a machine or some kind of assembly line that's running. If we're using all capacitor proc switches, you see what can happen. Somebody can just walk up and make the proc switch with anything, pretty much. Yeah. So if we're detecting metal parts, and you go up and make the proc switch, it's a capacitive proc switch.
Well, one has a greater range than the other.
Yeah.
The proc switch, I think, has a shorter range than the inductive.
Is that what it is?
Yeah. So although you could walk up to it and probably make it, I mean, you have to put your fingers or whatever it is between you and the moving part. Whereas magnetic would be a little bit, you know, if you got more distance.
Yeah, yeah. What's some of the problems that can happen with a proc switch? Some of the common problems, you know?
Put the wire together.
Wire,
When you get hit up there.
Like it's crushed or smashed.
it's smashed, it's crushed, yep,
Goes bad.
yep, it shorts, or whatever, opens, yeah. That's right, real common. Or it gets replaced at some point, and the adjustment isn't, you know, either it might be out of range, another common problem, or it's too close to the part and it finally just rubs the head off of the proc switch and shorts it out. Yeah, yeah, very common, very common. So without getting into a whole ton of the theory behind this stuff, the inductive proc switch, it's electromagnetic. And capacitive is electrostatic, and that's all based on that capacitive theory stuff that you guys learned in 117, 118, and 201. 201. Anyway, so both of them are pretty similar. There's an oscillator inside these things. Here's the proc switch. That's the head of the proc switch, that's why, whatever. But there's an oscillator inside. Everybody know what an oscillator is? It basically converts DC to AC. So there's basically this going on, not that you're seeing it, but that's what's going on. And in a capacitive type proc switch, in an inductive type proc switch, this signal's real high until we detect the part. And then the signal drops off way down because we're changing the electromagnetic, whatever it is. You know what I'm saying? We're changing the amplitude of the oscillator by changing the inductance of the circuit that's inside of it. If you go back, you know what a tank circuit is? No. No? It's a circuit that sets up a frequency, and that's basically an oscillator circuit. So we're changing the inductance of this coil that's inside this thing when a metal object gets close to it. Yes, that's right.
You said an isolator changes voltage from DC to AC or AC to DC?
DC to AC, yeah, that's an oscillator. And you basically have the same thing going on in the capacitive type, except what happens is you're changing the dielectric of the capacitor, which is changing the capacitance value. Remember dielectric, you have air, that's one of them, mylar, ceramic, tantalum, yeah, it's been too long ago for me. I know you guys just came out of 117 and 118, so you know this stuff. Another point that I want to make. Anyway, so without getting into all the theory of this stuff, that's basically what's going on. We also have photoelectric sensors. What are the two types of photoelectric sensors? Retro, reflective, and what else?
Repeat.
Yes, rubine. What's the difference?
Retroreflective is, it senses the light being reflected from an object that it's sending out.
Yes.
The through beam is like a laser where there's a sensor on both sides, it's picking up the other side.
And they're in a machine, huh?
Yes, that's right, yeah.
The
So
refrigerator will send it down and receive it.
Yes, that's right. So reflective, you have both a transmitter and a receiver built into one package, and then it sends a beam out to a reflector, just like you've seen the round reflectors. And then it's reflected back to the receiver. Through beam, basically the same, except you have the transmitter in one package and then the receiver in another, right? What's some common problems with these things? Yeah, it gets dirty, the lenses get dirty, the reflectors get dirty, out of alignment.
Transmitter goes bad.
Ton of stuff, yeah. Get hit by a fork truck on the way by.
ESD.
Are you saying that these are on the through beam, you're saying these are not in the same unit, but they're two separate parts?
Yeah, that's right. You have the transmitter in one and then the receiver in the other.
So that's like a reflective pad?
Yeah, that's right.
If they're,
Oh, no, I'm sorry. It doesn't reflect what's happening. All this is doing is sending out a signal all the time. That's right. And then this is wired into a PLC or something.
The through beam is like kind of like doing something like
Yeah.
yeah, what's this they were Baylor, like Baylor, like that for the
Oh, were
entry
you
class.
for like passes? I know shop. Oh, I'm not good. After all this, something like
Back to the proc switches. Let me back up for a second. Something else you need to be familiar with. There's also 2-wire and 3-wire, right? Proc switches? Yeah. So the 3-wire procs, it's something like this. 3 wires. This is the load. In our case, this output would go to a PLC. And what happens when the proc switch is made, it's basically taking this load to it's like a switch inside. It's connecting the load to the power, to the positive side of the switch. Yeah, it's activated. And then a 2-wire, it runs the load in series with a common. So which one's going to work better with a PLC? Yeah, 3-wire. So we're not going to work too well. It will, but I think 3-wire is probably the most common in my experience. I don't know what the book says, but in my experience, we always use 3-wire processors. What else? Ultrasonic sensors. What's that?
Send out sound waves.
Yeah, that's exactly right. Sends out sound waves like sonar, yeah. And it's generally used for measuring, like the volume of liquid in a tank. Kind of like a level switch. Kind of like a level switch. There's also a another sensor that's pretty common in any kind of testing type stuff. If you're testing engine components, transmission components, that kind of stuff, it's called a load cell. You guys run across something like that in your, okay, there we go. Well, a load cell, do you remember the Wheatstone bridges? It's kind of based around that principle. In fact, it is based around that principle. Except it uses, and if you remember the Wheatstone bridge, there's the Wheatstone bridge, and the principle behind it is all resistance values are balanced, right? So ideally, the voltage at this point is going to be 0 volts, right, in the center of that thing. That's kind of what it's based on. Except in a load cell, it's a resistor, but it's a strain gauge, which is basically like a piece of mylar, if you've ever seen them before. It's got a bunch of copper traces, a single copper trace. It's just
long.
Yeah, it looks something like that. And then what happens, oh, put it all out. Try that again. So what we do is we replace one of the resistors with a strain gauge. And the way the resistance changes on this thing is it flexes. As it flexes, the resistance changes in this copper trace. You see a lot in like research and development stuff. We used to use it a lot in engine testing, engine research, and that type of stuff.
It's testing physical load.
Yeah, kind of, yeah. We checked a lot of different stuff, like the force on the push rods inside of an engine, or the amount of torque on a crankshaft or camshaft.
The physical force load.
Yeah, that's right. So as this thing twists and flexes, obviously the voltage output here is going to change, right? And depending on this voltage, you can equate it to some kind of strain or stress or load that's being applied. Temperature. What's a common temperature transducer? Yeah, that's the most common one. Of course, there's J-type, K-type. J-type for normally lower temperatures, K-type for higher temperatures. There's RTDs. Thermistors, yes. Thermistors. Yeah, thermistor, which is a resistance type. Yeah. As the heat increases, the resistance increases. Same way with RTD. I never can remember what that stands for. Resistance temperature detector. Flow transducers. Has anybody been around flow transducers at all, or seen anything? So let's say we want to measure like the flow of liquid or hydraulic flow or flow switch. Yeah, flow switch. Yeah. Yeah, that's exactly right. Yeah. Very common. Of course, these days a lot of them are electronic. Very common though is there's some kind of a little turbine that's spinning It's spinning as we get flow. And inside here, there's a magnetic pickup. So as this thing spins, this magnetic pickup, it's detecting a signal, right? And this signal off of this magnetic pickup, it's just a bunch of pulses. So depending on the frequency of the pulses, we have more or less flow. Yeah.
That's what your water meters, you will find a lot of water meters for home use. When the city drives by to see how much water you've used, if they don't get out of their car to go in your fence where your mean vicious dog can rip their leg off, it's most likely because they have a water meter that has the same setup. And all they got to do is point a receiver at it, click it, it takes the frequency, and then they charge you according to your water usage.
There you go.
What's that little magnetic thing called?
Magnetic pickup.
Magnetic.
Yeah, it's just a little magnet. Yeah. And then these are little metal. So as this thing spins, of course, it's throwing out pulses, output, pulses.
So what do you call it?
A flow meter.
Okay, then the bullets like how the, I was looking at the turbulent type flow meter.
Yeah, that's what it is. Turbine type flow meter, yeah.
The funny thing about it is people try to be slick and flip their water meters around, thinking it runs backward. But the thing is, it's still counting. They don't understand it, but it's still counting pulses. No matter which way it goes, it's still counting 1 0 1 0 1 0.
That's exactly right. Yeah. Yeah, that's right. What else we have? Tachometers. Everybody knows what a tachometer is. You see them every day you get in your car. Don't you? Checks RPM, whatever. So it's a way of checking speed. Tachometer. And normally those are based on, there's a little magnet on a shaft, right? It's doing the same thing. It's sending out pulses. So know the speed, you know, kind of the same principle. Speed detection, position. Every machine tool has some kind of a position sensor on there, right? Encoder, resolver, that type of stuff. An encoder does the same thing. It sends out pulses. And there's rotary encoders and linear encoders. Somebody that's been out there know or are aware of this stuff. And how the encoder works. That's a lot of noise. So the encoder, here's a motor. Generally the encoder is mounted on the back side of this motor, and there's a small shaft coming out. Well, this encoder looks like a small little motor itself, kind of, but it's a generator, is what it is. And it's generating pulses. Inside this thing, there's this round glass disc. It's got a bunch of lines on it like this. And it's got some photo optics inside this thing. It's got an LED and then a photo transistor. So what's happening is this is making and breaking the LED light. So the transistor's turning on and off, on and off, on and off. It's like a switch. Except the package is kind of looks something like this. LED over here, and then the transistor, the photo transistor over here, and then this disc spins inside this thing. It's making and breaking that path of light. rotary encoder and linear encoder. Linear encoder is the same principle, except it's a long piece of glass. Well, we use a long axis of the
Is there a transmitter on the bottom?
It's a trend. If anybody's around the machine tool world, there's a lot of that, there's a ton of that stuff out there. Yeah, you're counting pulses. That's right. And the way they're rated is this encoder might be rated at, and this is strictly an example, 1,000 pulses per inch. Or per revolution. See where this is going? So every time you move an inch, you're going to get 1,000 pulses out of this thing. That's how the machine knows what position you're in. We count 1,000 pulses. Okay, we just moved an inch. Output control devices, solenoids. Here's something to take note of. An actuator is any device that converts electrical energy to mechanical energy.
What page are you on?
I'm in my notebook.
112.
Actuator. It's in the book, but I don't know where's that.
Output control devices are on 112.
Sam, could you repeat what you said?
Actuator, any device that converts electrical energy into mechanical energy. So what's some examples of actuators? One drum solenoid, a cylinder, a motor, electrical to mechanical energy. Any of that stuff. And there's something else we need to talk about here. I wanted to take you out to the machine out there so we can actually put our hand on this stuff. Let me talk about one more thing. We're going to take a walk out there and move around a little bit. Just so you can see this stuff where it's actually used. A lot of you haven't. And I get that. So we talked about, it's been a while ago. And he's making a lot of noise out there.
Sorry.
Can we do something like that in relay logic?
No.
No. Something we talked about a while back. And can we do something like that?
Nope.
In PLC logic? That's right. No. Now, I'm going to have to rewind because there's one instruction where that you can do that. You have to do that. That instruction is the output latch instruction. Output latch, output unlatch. Something we're going to be working with, except, and that's when you have to do it. And here's the reason for these instructions, is because back in the day, they used to have latching relays, latching mechanical relays. This would be the latch, and they actually had two coils in it.
And it would be the same relay?
Yes. So we had two coils in these things. We had a latch coil and an unlatched coil. So as soon as we latch up, the contact closes, right? Contact closes as soon as we latch up. It's just like energizing a relay. And what can happen is, let's latch it up. The limit switch closes, we latch up. It just has to close just a split second to latch this coil up. And then it can drop out again. This contact stays closed. Make sense? Yeah, that's a good way to think about it. It's like a memory. Yeah.
So latch doesn't need a ceiling then?
Right, it doesn't need a seal. This is like the set reset in Siemens. Yeah.
Okay, so, say it again. See how one latch it closes up, but see how one at the bottom, I have like a little memory to say up close a little bit?
That's right. It'll stay closed indefinitely until you energize the unlatch. And here's the key to this thing too. Once you latch up, let's say we latch this thing up, the power goes down. It stays latched in, that's right. Power comes back up, it's still latched up. Yeah. That's right. Yeah.
So, you're saying that no matter what you do, that stays closed?
Yes, until we energize the unlatch coil. Yeah. Here's where the instructions come in. So, let me do this. And then something I want you to think about. MS1. MS1. Motor starters don't have two relays in them, or two coils in them, but just for demonstration purposes. So we have a motor starter, a latching and unlatching motor starter. Is that a good idea? Why not?
Or you could just that unlatches it. Okay, be left on if it unlatches nothing.
That's absolutely
Because
right.
you can eventually run out your current's either gonna have too much or your conveyor or whatever you got running, it's not gonna stop, you're gonna have over travel.
That's right. So what can happen, we latch up this motor starter, the power goes down, right? When power comes back up, this machine's immediately going to take off, wherever it's at. Yeah, because we've latched it up. So we have the same principle going on over here. Latch. And we have some kind of preconditions. It's a conditional run. We have to have it unlatched to unlatch it. But, let me do this. Let me back up in just a second. Is that something we want to do? Latch up real world outputs like that? Yeah. Yeah, you never want to latch up real world outputs, although, I say this, if some of the labs we're going to be doing next time, the author has you doing that. It's very very poor programming practices to do that. Because once it gets latched up, there's no way to unlatch it. Unless you do it the unlatch. And you don't want machinery running all over the place when you power back up. Big safety problem. Anyway, latch and unlatch. So yes, these should be a binary file. B300, B300. And you notice they both have to have the same addresses too, right? If you latch up, you have to unlatch with the same address.
So this only can be done in binary, not in a regular.
Yes, no real world outputs. But like I say, some of the labs you'll be working through next time, he has you doing that for whatever reason. I don't know why. He does. What time you got there, Bradley? Your watch. 11:05. Let's take a walk out here, and I want you to just observe and kind of put your hands on some of this stuff so that you can kind of have an idea where it's even used at.